We are still on connected particles without inclined planes. So we are going to consider this where when we have inclined plane, when one is above the other, but still inclined at a certain angle. So the diagram above, so they are giving us this diagram here, shows two slopes, upper inclined at theta and lower at 5 degrees to the horizontal, where sine theta is equal to a quarter. Particles A and B are resting and connected by a lighting extensible string passing over a pulley. Full stop. If the upper slope is rough and the lower slope is smooth, so this one is smooth and this one is rough. It's smooth and the system is in limiting equilibrium. Limiting equilibrium means the body is about to move, but the frictional force has already reached its maximum, but the body is still at rest, but it's about to move. Okay, find the coefficient of friction between body A and then the upper slope. So this is our body A. So after drawing that, we first put in what we expect. So we expect this weight is going to be, we get a mass times gravity. It's going to be having a reaction. Let us call it reaction of mass 2. Okay, even this one is going to be having the same. It's going to be having a weight there, which is going to be 3 times V. Then, if you dissolve this one, you are going to be having 2D cos 30 degrees. Then, this side, you are going to be having 2D sine 30 degrees. So can we resolve this also? It's a reaction. Let us call it a reaction of body of mass 3 kilograms. So to resolve this, we are going to be having now, this is going to be 3D, then cos theta, because we don't know this now, but they gave us that. Then it starts to resolve it in this way here. This particle, I'm going to do this. So this is going to be 3D sine theta. Okay, you know that now this plane is going to be having the same tension because it's the same. So this one is going to be having T, then here also T. I also expect T in that spring there, T, and then also here T. Okay. So because it's the body is inclined plane, you expect it to move downwards now because it's going to slide. If you leave that body there, it's going to slide no matter the way it's. So this one is going to slide in this direction. So that's where our acceleration is going to be, and then this one will slide in that direction there. That's where the acceleration will be this, and this one also will be that. But because this surface here is smooth, we don't have anything like friction. But this one, they know that's the upper one is rough. So expect friction. So this is going to happen because our section is in this direction, friction will be opposite. So it's going to be now mu, but it depends on the reaction of that body, R3. As simple as that. So after doing that, now the rest are very easy to handle. Let us start with the 2 kilogram mass. Because this one, we don't have anything like friction, we are not worried about our R2. So based on only the directions, so this one is when it's going our acceleration in that direction, our F going downwards. What is pushing us? You know that our Fr is equal to ma. Our Fr, the resultant force. So what is pushing it down is going to be here, by the way. Our G, we are going to take 10 meters per second square. So they are looking for that. So depends on the question what they want you to use. Now this question we are going to use this. Now pushing downwards we have 2D, then sine 30 degrees, then minus, we start this being opposed by this T, equaling to the mass which is 2, then the acceleration is 0 because the body is limiting equilibrium. A is 0. Because the body is in limiting equilibrium. That's why I'm having my k as 0. So from here, I can abbreviate our t as, when I take it inside, I'm having 2g, then sine 30 degrees. So this will be 2 into 10 into a half. And so our t from here is going to be 10 newtons. After having t, then this one is going to be easier for me. So now I consider here we are considering a 2 kilogram mass. Okay, when I consider now a 3 kg mass. So is that still sliding downwards in this direction? That's where our acceleration, the direction of acceleration is so important. So it means that now my resultant force still will be equal to m times the acceleration. So what is pulling it in this direction? We first of all have this t. So we have this t. Is there any, and then also this. So these two forces are pulling it down. So this and this. So plus 3d. Then this one is going to be sine theta. Then minus, there is a force opposing, which is going to be mu r3. It will be equal to the mass, which is 3, times the acceleration, which is 0. Okay, but what is my r3? From here, if I resolve this plane like that, it's that my r3 is going to be, because there is nothing like acceleration in this direction, so this means that these two are balancing. So this is equaling to that. So that will be equaling to 3 g cos theta. Now the question is, what is my theta? They told us that. Remember, they told us that from here, our sine theta was a quarter. So if I have sine theta as a quarter, I'll place it there, meaning my opposite is 1, this one is 4. And this will be root 15. If you do 16 minus 1 and the square root. So if this is my theta. So from there, I can abbreviate my cos theta as adjacent over hypotenuse. So I have it there. So substituting in here, I have my R3 as 3 into 10, then times root 15 over 4. So my R3 from here is going to be, that is going to be 37.5, 7.5 root 15 newton. So I have R3. Now, so when I take this side, I have now my t. Remember, our t is 10 plus 3 into 10 into our sine theta, which is a quarter, equaling to mu into our R3, 7.5 root 15. So what do we have here? We are going to have this is that times this 70 over 4. 70 over 4 equaling to mu into 7.5 root 15. And if you divide, this will be, if you divide there, our mu will be 70 over 4. Basically, you can see it's going to be divided by, so this is 17.5, or you can leave it and then replace it at once. So our mu from there is going to be, this is 17.5. So here I'm getting 0.6025. And that's going to be my coefficient of friction between the body A, this body A, and then this rough plane, and that would be the answer. So that's how we handle that. I wish you well. What I'm noting here, when we don't have friction, You don't need the resultant in most cases if you don't have friction. We always use this is that as a equation when we have friction. And always friction is opposite to the direction of the acceleration.